See, elimination reactions are those in which two atoms or two groups or an atom and a group are removed. Okay, two atoms or two groups are an atom and a group are eliminated or say removed. Okay. Now see, when these are eliminated, of course a new bond is formed. Okay. Now coming to the types of elimination reactions. Elimination reactions are classified mainly into three types. Alpha or 1-1 elimination. Then the second one is beta or 1-2 elimination. Similarly, gamma or 1-3 elimination. Okay, alpha eliminations, beta eliminations, gamma eliminations. Okay, now this beta is further classified into even eliminations, then E2 eliminations, and of course even CB eliminations, elimination unimolecular conjugate base reactions. So this is the overall classification of elimination reactions. Alpha, beta, gamma. Beta are further classified into E1, E2, even CB. Okay, let's see them in detail. Now, first of all, what are alpha eliminations? You know, alpha eliminations are also known as 1-1 eliminations. It actually indicates that in this particular case, whatever are eliminated, like I said, two atoms or two groups or one atom and a group are eliminated from the same carbon. Okay, so here the elimination is from the same carbon. Now, let me show you that. This way. Now we'll be eliminating X and Y from the same carbon. But how? See this. See, a bond is nothing but two electrons. You know, a fresh bond is formed between these two. And the carbon will be left with 2 electrons. This way. See, overall, it has 6 electrons around it. So this carbon is with sextet of electrons. It's called carbene. Hope you all know. There are different types of carbenes. Now this is alpha elimination. Then going for beta eliminations. See, in this case, elimination is from the adjacent carbons. Reason why we call it 1, 2. Right. Now, let us show the same thing. X and Y again. See, somehow this X is eliminated. I mean, is abstracted by something. Then this one comes here. As a result, this one goes off. So that is how X goes off without the bonded pair. I mean, in the form of a positive ion. X plus and Y goes off in the form of a negative ion, that is Y minus. So we get this thing. See, this is how alkenes are prepared. Next, go for gamma eliminations. Now gamma eliminations are 1, 3. In this case, elimination is from first and third. Eliminated from the first and third carbons. Let me show you. Now these two are eliminated and you get this. A cyclic compound is what you get. When X and Y are eliminated, a fresh bond is formed between these two. Okay, so this is about the different types of eliminations that we have. Now going for different types of beta eliminations. Okay. See, within this we have E1, E2, and even CV. First, it's E1. You know, E1 refers to elimination unimolecular. Okay. Elimination unimolecular. I'll tell you why. Taking the mechanism into consideration. See, here the mechanism is of 2 steps. Since step 1, ionization occurs. Let me show you. See, this is an alkyl halide. In the first step, the halogen atom goes along with the bonded pair. This occurs in the presence of a solvent. So this step is also called solvolysis. The solvent here acts as a weaker base. And you know, this step is the rate determining step or the slow step. Now, what do we get? H, then this one. Because X minus is last, we get a carbocation. See, here the intermediate is carbocation. When the intermediate is carbocation, we know that rearrangements occur. Along with this, of course, X minus is last. So very important is carbocation intermediate. So rearrangements occur. I'll give you examples. Yes. Now going for the second step. Not so special. Only thing is here, using a weaker base. See, in E1, we use a weaker base. This hydrogen is abstracted by a weaker base. Then the bond goes to the rescue of the positive charge. So the positive charge is neutralized. Okay. Now, you get alkene, then B minus, which has abstracted H plus, is obtained in the form of BH. Let me actually clear you two things here. This step, of course, is fast. Let me just clear you two things. One is, what is a nucleophile and what is a base? Remember, both the nucleophile and the base are electron pair donors. Both, of course, donate electron pairs. But the basic difference lies in the point that the pair of electron is donated to an electron deficient carbon in case of a nucleophile. An electron deficient hydrogen, that is H plus, in case of a base. You know, we call a species as a nucleophile if the pair of electron is donated to an electron deficient carbon. I mean C plus carbon which has got a deficiency. Now if the same pair of electron is donated to an electron deficient hydrogen, I mean to H plus, we call it a base. Both are, of course, electron pair donors. Look at this. But here the donation is to an electron deficient carbon. Only then we call it nucleophile. If the same pair of electron is donated to say H plus, we call it a base. Okay, so this is very important. Now, let us go back to E1. Coming to the characteristics of E1 reactions. See, the first one is, in case of E1 reactions, rate depends on the first power of the concentration of alkyl halide, but not on the concentration of the base. So rate is proportional to concentration of alkyl halide to the power 1. Okay. That means when the concentration of alkyl halide is doubled, rate is doubled. That is how the power is determined as 1. Because when concentration of alkyl halide is doubled, it was observed that rate is also doubled. That is the reason why the power 1 is written here. See, this power or the order is determined experimentally. Okay. Base to the power 0. No, rate is independent of the concentration of the base. I told you this. Here we use just a solvent, which of course acts as a weaker base. So let me say that this actually follows first order kinetics. Okay. Now the second point. See, this reaction is called unimolecular. Because in the rate determining step or the first step of the reaction, there is only one molecule participating. Look at this. In the rate determining step, only one molecule participates. Therefore, it is unimolecular. So this is E1 or unimolecular. Okay. Yes. See, in this case, a good leaving group is required. Why is a good leaving group required? And what is a good leaving group? Let me give you an example. Taking the hydrogen halides. HF, HCl, HBr, and HF. Okay. Now, among these hydrogen halides, HF is least acidic, whereas HI is most acidic, right? That means from here to here, acidic nature increases. Now we know that the conjugate base of a strong acid is weak and vice versa. A strong acid has a weak conjugate base and of course vice versa. Similarly, a strong base has a weak conjugate acid and vice versa. Okay, now let us consider the conjugate bases of these hydrogen halides: fluoride, chloride, bromide, iodide. I mean, when they lose the proton or when they leave, they'll be leaving in this format. They'll be leaving in the form of halide ion, X minus in general, right? Now coming to this, see, because HF is a weak acid, its conjugate base is strong. So this is a strong conjugate base. What do you mean by a strong conjugate base? You know, a weak acid is the one that does not donate a proton readily. Right? That means it doesn't want to lose its proton. A poor proton donor, it wants to keep a H plus along with it. But still, if H plus is lost by some means, or if it becomes F minus, it will not be happy. It will again be looking for H plus to come back to it. Reason why we call it a strong conjugate base. What do you mean by a base? Base is a proton acceptor. This all is according to Bronsted-Lowry theory. A strong conjugate base is the one that accepts proton readily, right? It doesn't want to lose a proton, but by some means, if at all it loses a proton, it will be ever ready to accept a proton. Till then, it will be under a kind of unrest. So is unstable. Not that happy. Even while leaving it is not happy. After leaving it is not happy. So it's not that stable. F minus is not that stable. Now coming to the second one. Hi, which is a strong acid. What do you mean by a strong acid? Donates a proton readily. Right? Doesn't want proton. So it is very much ready to lose it. So the resultant I minus will of course be very happy without H plus. Even that is very clear from this. You know, it's a weak conjugate base. What do you mean by a weak conjugate base? Poor proton acceptor. It doesn't want proton. So has donated proton readily. Once the proton is lost, it is very happy. See, fluoride was not that happy, but I minus is very happy. You know, a good leaving group is the one that is very happy after it leaves. Point number one. So who is happy here? I minus. I minus is happy, so is a good leaving group. Right? A good leaving group is the one that, let me say, leaves happily. I mean, goes off happily. Point number one. F minus, as I said, is a poor leaving group. It doesn't leave happily. It has not left happily. It always wanted H plus to be with it. Point number two, see, because fluorine is more electronegative, as and when it leaves the substrate, let us say the alkyl halide, when the alkyl fluoride loses fluorine in the form of F minus, see, the resultant thing will be very much deficient because fluorine comes out along with the electron density because it is more electronegative. You know, being more electronegative, fluoride comes out taking more and more electron density and making its owner, making the substrate more and more deficient. Right? But whereas I minus, being less electronegative, does not make the substrate more and more deficient. So, simply speaking, a good leaving group is the one which is a weak conjugate base. Right? So this is very important. Now coming to the type of solvent used here. Polar protic solvent is used. What do you mean by a polar protic solvent? And what is the use of this? See, polar protic Solvent is the one that has a hydrogen atom attached to a highly electronegative atom. Like for example, see in water, there is a hydrogen attached to a highly electronegative oxygen. Similarly, in liquid ammonia, hydrogen is attached to the highly electronegative nitrogen atom. Now, what is the role of a polar protic solvent? You know, the polar protic solvent stabilizes ions formed in step 1, that is ionization step. We get a carbocation, we get a halide ion. Carbocation, C plus. This C plus, of course, forms bonds with or is stabilized due to the non-bonding electrons on oxygen atom, the positive one. Whereas X minus, the halide ion, it gets stabilized by the partial positively charged hydrogen. So that is how the ions are stabilized by the polar protic solvent. In fact, the non-bonding electrons on oxygen and the partial positively charged hydrogen stabilize the ions formed. So this is the role of a polar protic solvent.